Is it? Is there a V2 on that, or just okay, fine. Nope, still morning, so good morning, everyone. As the title indicates, I'm going to talk about a method for reducing anthropogenic heat in urban areas through use of two heat sinks, the sky for radiative cooling, and then ground heat sinks. As we know, the built environment can play a major role in climate change mitigation. For operating energy of buildings, that's clear. They're responsible for about 28% of global carbon emissions. We can also include the embodied carbon that is associated with the construction of buildings, and that's another 10%. And there are upward pressures on both of those, as shown to the right. Buildings also have a role in adaptation, where we focus on heat resilience, picking up in the last talk, where either in the presence or absence of electricity that could be used for mechanical cooling. Air conditioning systems, which are ubiquitous worldwide and often justifiably so, are a decontextualized solution to this, to say thermal comfort. They're the same the world over. They're energy intensive, carbon intensive, and because in many cases the heat is rejected into the urban canyon, they raise urban temperatures. Passive strategies, either purely passive or with, say, low energy ceiling fans, can help in some climates. Envelope upgrades, shading, thermal mass, and then ventilation. Not in all cases. So what I want to focus on is low cost, low energy cooling systems that do not use the vapor compression cycle. So the typical air conditioning. And I've listed 4 here, but we're just going to talk about 2 of them. The pointer is not great. One is, well, both assume that you have a cooled slab that has water pipes in them. And now where does that water go to reject the heat that's picked up, removed from the building air? For the radiator system, it goes to the roof, with the radiator on the roof to reject that heat to the night sky. The geothermal system, it goes to the ground to another heat exchanger that's associated with the structural footings for the building. We do not consider evaporative cooling and district cooling. Radiative cooling, all objects radiate heat to the, well, essentially through the atmosphere to the universe. That can be reduced due to cloudiness and relative humidity increases. And the urban morphology also plays a role. As buildings are more densely arrayed in cities, the sky view factor for a particular roof goes down, and that will reduce the heat exchange. We're considering the kind of system shown on the left, which is just a standard have pipes and then maybe fins to improve the heat transfer surface, and use that only at night. On the right are daytime systems. We've seen some of that in the posters, which can reject, due to various coatings, reject almost all of the short-wave radiation, 97% plus, and be effective during the day as well. For ground cooling, it's well known that as you increase in depth going down, the temperatures approach a constant value, which is the annual average of the ground surface temperature. And that exponential convergence can be modeled as a function of soil properties, thermal diffusivity. So as a function of depth and time of year, the ground temperature can be reasonably accurately modeled, and we make use of that. For our purposes, we're using a shallow geothermal system where the heat exchanger is constructed to be associated with the footings. The maybe more common boreholes, or say for ground coupled heat pumps, are shown on the right. So our approach here is to answer a question: can we leverage the building's structural system as, say, the scaffolding for effective heat dissipation. So that's the slabs and the footings. And you see on the right that for the roof, the concrete is supporting a layer of insulation, and then the heat exchanger, and on the lower right, the heat exchanger is underneath the pilings. We do this in a multi-domain simulation framework. There's a lot in this slide, but we have a massing proposal on the top left. There we go. How close buildings are to each other, structural system design that we can optimize. We look at sky dissipation, dissipation to the ground, compute the cooling loads as a function of envelope properties and internal gains, and then evaluate the heat sinks. And for all of this, we're computing the amount of energy that's transported to these heat exchangers and then, say, removed from the building. Oh, I'm sorry. Where is it? Oh, this one and not the hand. Yeah, apologies, because it's being recorded. Okay, I'll stand here. But it's not advanced on this screen. Where's the hand microphone? Thank you. Yeah, apologies for not using this. Better? Okay. Yeah, thanks. Okay. So this is a fairly standard flow of energy through a heat exchanger. There are two heat sink terms there, effectivenesses that modulate what you would get, say, from standard heat exchanger design, the finite size of the heat exchanger, and then how close you get to your, say, the sky temperature is a function of a couple of other things that we'll show here. Can you cool water on the roof all the way to the sky temperature? And no, for two reasons. One is the sky view factor, which shows up in the this term, which is less than 1. And the other is that we're also getting some convective heat exchange as well as the radiative heat exchange. If there were no convection and the sky view factor were 1, then we could cool the water all the way to the sky temperature. Okay. And for the ground, we have means of calculating the annual average ground surface temperature, accounting for urban warming. And we need the ground surface temperature is the annual average air temperature. 5 minutes left? No. Yeah, thanks. And then it's reduced some by the long wave radiation from the ground, increased some from the short wave absorbed radiation. And we can calculate those as a function of the urban geometry, just looking at how the sun affects those surfaces. Okay, here are some results. We did this for 3 cities, Algiers, Cairo, and Bangkok. And for each, we considered 135 combinations of the width of the buildings and their height varied in kind of 1 meter increments. And we calculated how much of the total cooling that was needed could be dissipated through these passive means. You can see the orangey are due to the ground, the sort of muted purple are due to the sky, and then the gray is the total. So in Algiers, we can get, as a function of a wide range of floor area ratios, density, we can get rid of all of the cooling needed. Less so in Cairo, although maybe 50–60% for low density cities. Bangkok and Southeast Asia, this doesn't work at all because of temperature, ground temperature is high, and humidity in the air. And you can see 3 densities flagged there. This one looks at the structural carbon on the y-axis and the cooling carbon over 50 years on the x-axis. The structural carbon is the same in all 3 cities, the body carbon and materials. But going from Algiers to Cairo to Bangkok, the cooling needed, the operational carbon, as you can see, greatly increases, and it's more impacted. It spreads more, so it's more impacted by the density of the cities. As the cities get denser, the operational carbon increases. There's less opportunity to to get rid of it. As a function of floor area ratio, things get a little bit better if the building occupies more of the site. The ground area ratio, the lambda p that we often look at in urban climate studies. That's because you're having more footing area and you can reject more heat to the ground. Okay. Even if this can't remove all energy from the building, it can remove a significant amount, and particularly in shoulder months, as shown in Cairo. And one other thing, although it's only at the 1% level, but it's interesting, the total is 6.13 and then 6.08 on the other side, slightly lower, and that's because that takes credit for not dissipating heat into the urban canyon, and whereas that in turn would increase the building cooling load a little bit. And I think, oh yes, one last one. This maybe belatedly shows the workflow environment for this study. This was done in Rhino CAD program and visual scripting language Grasshopper. Might have mentioned that earlier. So all this has been coded, but it's set for users in educational and professional environments to use, and one can adjust the height and the location and the width of that building in the middle, and also the size of the surrounding buildings. And then what comes out of that is a monthly set of bars. The blue are the total cooling, and the yellow is what's dissipated to the ground, and the red is what's dissipated to the sky. And with that, I thank you, and I'm happy to take some questions.
Sure. We might have time for two questions.
Hi, Professor. Thank you for your presentation. I wanted to ask about the humidity effect in the results. Because for a lot of cities, especially in hot and humid climate, air conditioning acts also as a dehumidification means, so that indoors can maintain thermal comfort. So I was wondering how much of the passive cooling can deal with humidity in those climates.
So the question concerns humidity? Yeah. That's go back behind the mic. Humidity is a good question. So a couple of things I could say about that. One, the cooling system that's used that I've shown you has certain efficiency advantages, but it's a sensible cooling system in the slab, so that does not remove humidity, and that humidity would need to be otherwise removed with desiccants or vacuum membranes or a conventional system that is only doing the latent cooling. And this is focused entirely on the sensible cooling. So that would be separate. Another thing one might ask is, well, if this only removes 50%, do I have to have a separate system for the other 50%? And my thought would be that one simply has heat pumps to augment, to take heat out of the water loops if it's not rejected to the ground or to the sky.
Thanks for your impressive talk, Professor. I got curious. If we dissipate the waste heat from air conditioner into the shallow ground, is it possible that, because this heat will not disappear, is it possible this heat will finally conducted to the land surface and finally convected to the atmosphere and also will increase the outdoor air temperature? Thank you.
Yeah, so that's also a good question, and I had one little note on one of the slides that attempted to address that, although I didn't cover it in my talk. The premise of this was heat rejection, but ground is properly considered as a seasonal heat storage and not rejection. It's not like dissipating it to the night sky. So what one does with that is strongly a function of climate. If it is coolish in the winter, then over a year, the heat that's dissipated, put into the ground in the summer, can come out in the winter just by conduction and be balanced. If not that, there needs to be some way of getting it out, and that could be having a heat exchanger that then just brings it up to the ground surface and dissipates it into the cool air. But all of that is one reason why Bangkok doesn't work at all, and that's embedded in this.
Thank you very
Yeah.
Thank you. All right, our next speaker is TC from PLL, talking about afforestation in cities. Let's welcome.